SwayamPrabha. Digital India. Educated India.
So, now I am going to do an example where we just to begin with we consider a mass spring system. Okay, let us say I apply a force f of t and let us say we get the displacement x of t, the spring being some k. Okay, let us say we have a frictionless surface, right. So, we already know that the governing equation is going to be mx double dot plus kxt is equal to f of t. Okay, the plant transfer function is going to be x of s divided by f of s is going to be 1 divided by ms square plus k, right. These are things which we already know, right. So, just for simplicity, let m be 1 kilogram, okay, and k be 1 Newton per meter, okay, just for simplicity, right. So, this implies that the plant transfer function is going to be equal to 1 divided by s squared plus 1, right. So, the poles of the plant transfer function are going to be at plus and minus j. So, is this system Bibo stable? Yes, no? So, what did we discuss? Like if you have non-repeating poles on the imaginary axis, like for one class of inputs, the system output is going to blow off to infinity, right. So, in this example, for what input your system output will go to infinity in magnitude? Cos t and sin t, right. So, for imaginary roots, the if you have a sinusoidal input whose angular frequency is going to be the magnitude of the pole, our output magnitude goes to infinity, right, as t tends to infinity. That is what we have, right. So, so we want to stabilize the system, right. So, let us design a PD controller. Okay, like if you recall, we did one problem like this, the proportional controller does not work. So, we saw that PD controller works for such cases, if you recall from what we did previously, to stabilize the closed loop system, right. Stabilize with negative feedback, okay, let us say with unit negative feedback. Okay, stabilize the plant with unit negative feedback. Okay. So, that means that C of s is going to be equal to KDS plus KP, right. So, let us say I pull KD common out of the term. So, I get S plus KP by KD, right. Okay. So, let us consider the ratio of KP by KD as 10 just for an example, and let us say I call KD as K, so that I do not need to write the subscript D all the time, right. So, what we have done, so let KD be denoted by K and KP by KD be equal to 10. So, if we were to draw the block diagram, what would that be? So, I have a plant, okay, we have an input and an output, we have a controller, right, we have a summing junction, we have a reference input R of s, this is E of s, this is U of s, this is Y of s, and then we have unit negative feedback, right. So, what are the what is the plant transfer function? 1 divided by s squared plus 1. What is the controller transfer function? K times s plus 10. So, this implies that what is the open loop transfer function? K times S plus 10 divided by S square plus 1. Okay. Now, the question that we are asking ourselves is that plot the locus of closed loop poles for k greater than 0. Okay, that is the question we need to answer. Okay, I hope it is clear how we are formulating it as a root locus problem, right. So, this will be pretty useful for us, right, because I want to see how the root locus varies, right, the closed loop poles vary as I change a controller parameter. See, previously using Routh's criteria, what we did? We only got ranges of the controller parameters that stabilize the closed loop system, but now I want to look at more things, right. I want to see how the branches traverse in the complex plane as a variable parameter, so that I can design my controller in a better manner, right. So, that is the advantage of root locus. Okay, that is how we are going to use it for control design. Okay. So, I am taking very simple examples so that we can work them out by hand, right. So, see, if I take a higher order system, hand calculations are going to become more challenging. Okay, that is why I am taking second order systems to illustrate the point. So, let us run through the steps. Okay, like you tell me what would be step 1. What is step 1? So, step 1 is to first determine the or locate the open loop poles and open loop zeros. So, in this example, the value of n is 2. What is the value of m? 1, right. And what are the open loop poles? Plus or minus j, and we have an open loop 0 at minus 10. So, first let's mark those. Okay. So, let me first extend this to minus 10. So, let us say like I have a 0 at minus 10, okay, and then I have an open loop pole at plus j and minus j. Okay, those are my open loop poles and open loop zeros. Okay, fine. Now, what is step 2? What is step 2? Step 2 is locate the part of the real axis that lie on the root locus. So, if you look at the real axis, are there any open loop poles or open loop zeros on it? There is one, right. There are no open loop poles on the real axis, but there is an open loop 0 on the real axis, and that cuts the real axis into 2 subregions, right. What are they? Minus infinity to minus 10 and minus 10 to plus infinity, right. Now, the question is that like which part lies on the root locus. To figure it out, what will I do? I choose a test point ST1 here and I look to the right. How many open loop poles and open loop zeros do I have? 1, which is an odd number. So, minus infinity to minus 10 lies on the root locus. What about minus 10 to plus infinity? I look to the right. Let us say I take a test point ST2 in the region from minus 10 to infinity. I look to the right and there are 0 open loop poles and open loop zeros, right, to the right of it. So, this region does not lie on the root locus. So, the only region that lies on the root locus is the region between minus 10 to minus infinity to minus 10, right. So, that is the only region. What is step 3? Asymptotes, right. So, there will be n minus m asymptotes. In this case, n minus m is 1. So, there is going to be 1 asymptote. Okay. And so, what is the angle of the asymptote? That is going to be equal to plus or minus 180 degree times 2k plus 1 divided by n minus m. Okay. So, that essentially becomes 180 degrees, right, because I do not have any other, right, n minus m is only 1. So, I need only one angle, which is 180 degrees, right. You can call it plus 180 or minus 180, anyway the angle will be the same. Now, the question is that, like, where is the asymptote? See, minus 180 degree means I can have lines parallel to the negative real axis, but where in the S plane? That will be answered by the point of intersection, although it is trivial, you know, like let's do this, right. So, point of intersection of the asymptote with the negative real axis is going to be what was that? Sum of open loop poles minus sum of open loop zeros divided by n minus m, right. So, open loop poles are plus n minus j minus sum of open loop zeros, that is going to be at minus 10 divided by n minus m. So, what are we going to get? Plus 10. So, what does this really mean? This really means that the negative real axis is the asymptote, right. See, the asymptote goes along the negative real axis. Instead of any line parallel to the negative real axis, the negative real axis is the asymptote, right. So, the asymptote, okay, is along the negative real axis. That is what this analysis can conclude. Okay. So, that is step 3. Now, what is step 4? What is step 4? Breakaway or break-in points. Okay. So, let's look at them. So, how do we calculate breakaway break-in points? We look at the open loop transfer function, right. The open loop transfer function is of the form k times A of s divided by B of s, right. So, what is A of s here? S plus 10. B of s is s squared plus 1, right. See, as I told you, you just need to follow the steps, okay. If you follow the steps methodically, you know, like we would be able to get the root locus, right. So, that is it, okay. So, A of s is going to be s plus 10, B of s is going to be s squared plus 1. Negative real axis, because the point of intersection of the asymptote with the real axis is plus 10. So, what is the only line which will intersect the real axis at plus 10 and still have an angle of 180 degrees with the positive real axis? So, the asymptote has to necessarily go along the negative real axis, right. Okay. See, what is an asymptote? The asymptote indicates the line along which the root locus will tend to as it goes to infinity, right. That is the meaning of asymptote. Now, when we say the asymptote makes an angle of 180 degrees with the positive real axis and intersects the real axis at plus 10, the only choice is the real axis itself, right. See, only the real axis, only if the asymptote is along the negative real axis, you know, like you can satisfy these two conditions, right. So, that is why the asymptote is along the negative real axis, right.
Plus minus 10 and the angle.
Yeah, plus minus, both are the same, right. I just took one, that is it, right. You can take plus minus 180 degrees, plus minus 540 degrees, does not matter, okay, you will get the same direction, right. So, yeah. So, okay. So, A of s is s plus 10, B of s is s squared plus 1. So, consequently, A prime s is going to be 1, B prime s is going to be 2s. And what is the equation that we need to solve for breakaway points? It is going to be A prime s B of s minus A of s B prime s is equal to 0. So, this would give me s squared plus 1 minus A of s is going to be s plus 10 times 2s is going to be 0. So, this will give us what? I will have minus s squared, then minus 20s plus 1 equals 0, right? Am I correct? So, can you calculate the roots of this equation and let me know? So, I can rewrite this as s squared plus 20s minus 1 equals 0. So, this implies that the potential breakaway points are going to be what? There are going to be two roots, right? What are the two roots? You will get the two roots as minus 20.05 and 0.05. Okay, please check it independently. Okay, so SB equals minus 20.05 would imply a K of 40.1. Okay, and SB equals 0.05 implies a K of minus 0.1. Right? How do we get this? K of s is equal to minus B of s divided by A of s, right? If you solve that, you will get this. So, by looking at this, which is a breakaway point? This one, right? This is not. So, minus 20.05, s equals minus 20.05 is it a breakaway point or a break-in point? In this case, it is a break-in point. I will explain why. Okay, where K is going to be equal to 40.1. Okay, that's why. That's what we will get from this analysis. Okay. Now the question becomes, why is this a break-in point? Because you can see that, see, I am going to have two branches starting from plus j and minus j. Okay, they are going to be complex conjugates, right? And ultimately, one branch is going to come and terminate at minus 10, right? Because that's one open loop 0. Another branch is going to go to infinity along the negative real axis, that is to minus infinity along the negative real axis. So, obviously, both points should intersect somewhere on the real axis, right? That is going to be at minus 20.05. So, two branches will come from the complex conjugate plane, hit at minus 20.05 and then go to one to the right, one to the left. Okay, so that is what is going to happen. So, in this case, what is going to happen is the following. So, you have an open loop 0 at minus 10. Okay, let us say I am not drawing to scale, but you get the idea, right? So, and what is going to happen is that you are going to have two branches which are going to start from the two open loop poles and come and hit the negative real axis at minus 20.05, and then one branch will go like this and one branch will go like this. Okay, that is why it is called as a break-in point, right? Because it breaks into the real axis. Okay, so that is why it is a break-in point. Okay, is it clear why that becomes a break-in point? Now, what is the next step, fifth step? What is step 5? It is to calculate the angle of departure, right? So, in this case, we need to calculate the angle of departure because we have a pair of complex open loop poles, right? So, let us calculate the angle of departure from plus j. What is the formula for angle of departure from an open loop pole? It is 180 degrees minus the sum of the angles made by the vectors from other open loop poles to this open loop pole, right? So, if you look at what is the only other open loop pole, see, we are considering plus j, right? What is the only other open loop pole? Minus j. So if I draw a vector from minus j to plus j, what is the angle made by that vector? 90 degrees. So I just write 90, there are no other open loop poles, plus sum of the vectors, angles made by the vectors drawn from open loop zeros to this open loop pole. What is the only open loop 0 here? Minus 10. You draw a vector from minus 10 to plus j, and what is the angle made by this vector? Tan inverse of 1 by 10, and if you calculate tan inverse of 1 by 10, so this, let me write it as tan inverse of 0.1, okay, tan inverse of 0.1, and if you evaluate this, this is going to come as, the answer is going to come as 95.71 degrees, okay, that is what you will get. So this is the angle of departure from the plus j pole. So what it really means is that, so if I consider the S plane once again, and if I consider the pole at plus j, the root locus is going to depart at an angle which is 95.71, right. So then what can you say about minus j? It is going to be symmetric, right, it is a mirror image. Why? Because you can only have complex conjugate poles, right. So you can immediately figure it out that the angle of departure from minus j is going to be either 360 minus this or minus 95.71, but anyway I will calculate so that like we will convince ourselves, right. So you have a 0 at minus 10, now we are looking at minus j, right. So what is the angle made by the vector drawn from the other open loop poles to this pole? It is going to be minus 90 or 270, okay, you can write it either way, let us write it as 270, right. Then what is the angle made by the vector drawn from the open loop 0 to this pole? It is going to be this angle, right, which I can write as 360 minus tan inverse 0.1, right, because I want to look at this angle, right. I take angles to be positive counterclockwise from the positive real axis. You can write it as either positive thing or negative minus tan inverse of 0.1. So if you calculate this, you will get the answer as 264.29, which is the same as calling it as minus 95.71. So I am just doing this to convince you that when you have a complex conjugate open loop pair, the angles of departures are just going to be negatives of each other, or they will sum to an even multiple of pi, alright. So that's important, okay. So they are just symmetrical about the mirror images about the real axis, okay. So that's something which we need to remember, okay. So what I want you to do is do the final step, okay, and then like construct the root locus, right. Final step, step 6 is the crossover point, right. So how do we get the crossover point? Consider the characteristic equation, right. Closed loop characteristic equation is going to be 1 plus k times s plus 10 divided by s squared plus 1 equals 0. So this is going to be s squared plus ks plus 10 plus k, am I correct? So 10, oh sorry, 10k plus 1, right. Yeah. So if I substitute s equals j omega in this equation, what am I going to get? I am going to get minus omega squared plus 10k plus 1 plus j times k omega is equal to, sorry, j times, did I do something wrong here? Is this correct? Right, j times k omega equals 0. So now if you equate both real parts and imaginary parts to 0, what do you get? See, k omega equals 0 means k can be 0, omega can be 0, or both can be 0. K equals 0 means, you know, like, see, this will give me two cases. If k is 0, from the real part, I will get omega to be what? Plus or minus 1. So plus or minus j is anyway the open loop pole. That's where I start when k is 0, right? I get the same answer. Now omega equals 0 implies k is going to be equal to minus 0.1, which is not what to say under consideration, because we are not considering k to be positive. So anyway, these are the open loop poles, right, plus or minus j. So in essence there are no further crossover points other than the open loop poles. So the root locus starts from the open loop poles and it remains in the left of plane always for all k greater than 0. Okay, so that's what we can figure out. Okay, so I will quickly draw the root locus. Okay, like you can go back and think as to how it came in this shape, and we will start our discussion from this point in the next class. Okay, so let me quickly finish that and then we will stop. Okay, so the open loop poles are at plus j and minus j, and we have an open loop 0 at minus 10. So what's going to happen to the root locus is that we are going to have two branches, okay, which are going to come like this. Of course they are mirror images of each other. Okay, they intersect at minus 20.05. Then I have one branch going like this, another branch going like this. Okay, so here k tends to 0 are the two open loop poles. The value of k at the break-in point was 40.1. So the direction is like this here, and it comes to an open loop 0 at k as k tends to infinity in both cases. Okay, so this is the root locus. Why should it take this shape? As I told you, like with experience you will get it. Like, and also please note that the closed loop characteristic equation is a second order polynomial, right? So it will take this particular shape. Okay, so we can't reproduce the exact shape by hand calculation, but it's okay. Like you draw an approximate shape. Okay, marking the critical points, right? Okay, so I will stop here. I know, like, we will discuss this once again in the next class, and then we will continue from here, right? But please think about the other two questions and come to the class for Monday. Okay, thank you.